Hey everybody, Lars here. It is 20 after 1 on Friday evening, and I wanted to make sure I got you your first review video for Unit 4, the one on sorting and searching. I am exhausted and my voice is tore up because I was just screaming and yelling. Hold on, I have some pictures for you. Boom, if you can see, that's really the beginning. Um, that's me right there. That's my buddy Daryl. And this was Wednesday night, the night before the party, planning things for my NCAA party. Then all my friends come crashing into my house, and we watch all of the NCAA basketball games. As you can see, we have 3 TVs set up in my living room. And all of my friends from high school and college, and most of the guys I played basketball with when I was a kid 1,000 years ago, come over to the house, and some guys even work from the party. We set up our laptops and we do our work during the day, and we watch all the basketball games. As you can see, we have all the NCAA basketball games on for the NCAA basketball tournament the last 2 days and all this weekend. So we do it for all 4 days. And then, also both days we all go out to breakfast. So that's most of the guys who played basketball from touching in the 80s sitting there at that table. And we're the one we just watch basketball all day long. So I am tired, but I know there is weather coming. So I want to make sure you have review videos and you have homework assignments so that you have something to do just in case you get snowed in late Sunday or you get snowed in on Monday. Hopefully over the weekend I'll also get you the second video in this series. But for right now, I want to go over the slides. And we have the beginning of your Unit 4 slides talk about sorting and searching. And I go through the thing with the sorting hat. The thing is, when you were a student taking computer science back in the 80s like I was, you take computer science for a month and you learn a little bit about data like you did and sequences and stuff. And then all of a sudden you get hit with sorting. And you have to do a thing called a bubble sort, and then a J sort, and then a quick sort. And you are hit with all of these crazy sorts. And for the first month or two of your existence as a computer science student, you're like, what's with all these sorts? And you really can't stand it. Now, because I was too young to understand what was going on, I thought it was ridiculous. But when you get older, you realize that sorting is a good way to show a young programmer or a young computer scientist the way different algorithms have different efficiencies. Some work better than others. Some have better ideas behind them to get things done. So that's why in the very beginning, sorting is important for people who are learning programming. Now, I am not going to force you guys to code a whole bunch of sorts. I have to make decisions because we only have 7 or 8 weeks to learn the basics of Python. Then we got to spend a little time doing CS stuff. Then we got to spend some time doing object orientation. So I've got to pick my spots. And one of the spots that I pick to save a lot of time is to not have you run through 50 different sorts, because what you're going to learn is that, well, you learn about why sorting is important, and I kind of just talked about that. And then you have this site here with the sorting algorithms. This is popular. People like this, and it'll show you how the different kinds of sorts, insertion, selection, bubble sort, all of those things work. Bubble sort is very inefficient. I doubt that they will ever make you do a bubble sort in any context. One of the reasons it's important is to show you efficiency of algorithms. The second reason it's important, and we're going to get to it in a little bit, is that it's good to have sorted data. And if you have sorted data, you'll see just the one example we're going to run through. You can do things much, much more efficiently than you could without. So when it comes to basic sorting, I just want you to be aware of the different kind of sorts, how they work, what's behind them. And I think this website is a really good place to go and learn a little bit about that. The reason I'm not going to drive you nuts about it is for the rest of your life, from now, when you're watching this video, until the end of your life, you're going to do what's in front of you right there. You're just going to run sorts on things because sorts exist in libraries and are waiting for you to run. And as you can see in this thing, if I create a list, I can just run a sort method on it and it sorts it. And you'll see here that I showed you a bunch of other sorts here. the one that Python uses is called the Tim sort, and it's actually pretty recent. It's an interesting story, so you have some time, go to Wikipedia and check that kind of stuff out. But real quick, you can see I create a list of numbers, and then I run the sort, and then I print it out again, and boom, it's sorted. I can do the same thing with alphanumerics. I can do the same things with strings. You can see I have a list, the order's all over the place. I use the sort, and I do that. Now, one last example is I can create a list, and as you know, one of the magic things about lists is that you can just fill it with different kinds of objects. You can mix and match your data types. Well, what happens if I take a list, string, integer, with a bunch of different data types, and I try to sort that list? I'll get an error. Because, you've heard the whole saying, you can't compare apples and oranges. Well, it's true. I got apples, strings, and I got oranges, integers, and I got different things. When I compare them to see, if one is greater than the other or one is less than the other, so I can put them in order, I can't compare the word Lars to 33. Now, if something tells me how to convert a string to an integer or how I convert an integer to a string, I could do it. And actually, Python does have ways that we can force things to be casted and then sort them. But at first, it'll just look at the list and go, look, we got to have something you got to tell me how to sort it if you want me to sort it. And, later, as you learn more about the language, there are ways to do that. But at first, in this simple example, sort just says, see ya, unorderable types. If you read the error, it says unorderable types because you're mixing and matching your data types, all right? Now, I just said the reason we care about sorting is because as we're young computer science students, we want to learn about the efficiency of algorithms. But the other reason we care about sorting is because we really, really, really need sorted data. And the reason we need sorted data, you're about to see, is because it makes our life incredibly easy. And it's a good thing and touches upon some data science concepts. The more things we know about our data, the more informed we're going to be about how to attack learning things from our data. And you'll see just now, as we look at searching, if I have a list, a simple list, and I need to know if a specific item resides in that list, but I don't know anything about the list, I don't know if it's ordered, unordered, crazy, what do I have to do? I basically have to look in every spot to see where my item is. Now, if I know there's one item, then I'll start at the beginning and I'll look. Is that the item? No. Get the next one. Is that the item? No. Get the next one. Is that the item? No. Get the next one. So let's say I have a list of 50 items. Potentially, in a worst case scenario, I've got to look 50 times at that list. Because if what I'm looking for resides in the last spot, then I'm going to have to look at every single item in that list. Now, if I get lucky, it might be in the second spot or the fourth spot, and then I only have 2 or 4 what we call lookups to find it. But we've always got to have a worst case scenario in mind, because if we really want to detail the efficiency of the things that we're doing as computer programmers with our algorithms, we have to assume a worst case scenario. That way you never get bit in the rear end. So you will always assume a worst case scenario when you look at the efficiency of algorithms and you analyze algorithms. So for a linear search, we're talking about however long the list is, or n, and we're going to get to that, what that means in a second, because that means something when we analyze our algorithms. Now, what if I have sorted data and I know my data is in order? Well, then searching for a particular item becomes easier, because what can I do? If I've got a sorted list and I want to know if a certain number is in it, well, what can I do? I can play high-low. I can go to the middle of the list and I can say, hey, is my number there? Let's say we have a list of 200 items and I'm looking for the number 307. Okay? Simple example. Well, I go to the 100th element of my 200 number list and I say, is this 307? And it says no. Then I said, okay, is 307 higher or lower than the number in the 100 spot? And then the search algorithm comes back and says 307 is lower. Then I'll say, okay, what does that tell me? if I know that my number is lower than the middle of the list, then I can throw away half of the list, okay? Because I don't need the bottom half of that list. I know for a fact 307 is not there because everything from 0 to 100 is lower. So then I can grab the list from 100 to 200. What do? Cut it in half again. And I go to the 150 spot, or what's now the 50 spot, but the 150 spot. And I say, hey, is this 307? And the program says no. And I said, okay, is 307 higher or lower than what I have there? And the program comes back and says, oh, this number happens to be higher than 307. So instantly, what do I know? Everything above that spot, I don't need. Because if it's higher than 307, then I know 307 isn't in there. I have a sorted list. So I throw away another 50 numbers. Now, in just 2 lookups, I've taken my 200 item list and made it a 50 item list. And you keep going down the line like that. And you'll see that if I attacked a 200 item list with a linear search, well, worst case scenario, I would have to look 200 times. Well, with a binary search, what I'm doing is I'm cutting the list in half every time. So 200 becomes 100, 100 becomes 50, 50 becomes 25, 25 becomes 12, 12 becomes 6. My worst case scenario in a binary search is like 8 lookups compared to 200. And this is a small example. What if I were looking at millions and millions of numbers? The savings would be insane. So as you can see, if you went through the slides and looked, I did a real quick 16 here. Every time we cut the list in half. And we can do this because we have sorted data. If the data isn't sorted, we couldn't do this. It wouldn't make a bit of sense. But because we can do this, we can take lists and instantly chop them in half. And the efficiency is nuts. And then I show you this code. Okay? Ready for an early gift? A birthday gift, if you will? See that code up there? It's already there for you to type in if you wanted to. But I'm going to give it to you because I already coded it up. And I'm going to give it to you with a little added value because I've got my binary search here. But I also real quick coded up a linear search. Because what are you doing? All you're doing is looking through a list until you find something. And if you find something, you break and then you print it. Okay? That's all. That's all a linear search is. Actually, what I should do is I should return the range, but I'll leave that for you to do. I just print it and break out of there. Okay? So I think, I don't know. Let's find out. If I run this, all right, what did I run it for? I ran it for, is that 1 million? Yes. I ran it for 1 million numbers. And I'm looking for, it's a worst case scenario. I'm looking for 999 to 999. And what happens? Here it is. Worst case scenario, it takes me 19 lookups to find it. All right? What's that 33? What is that right there? I did a linear search for 333444 in my nums. And how long did it take me to find it? Can you guess? 1 less is the index. Yeah, say 444, and that's 443. Because you start with 0. And then in that index number, you will find that number. And that's, it's an ordered list. So if you do a linear search in an ordered list, it's going to take that many numbers to find what you're looking for. So that makes perfect sense. Now, really quickly, that's a binary search algorithm right there. It's an easy thing to understand. It may look complicated when you first get your eyes on it. I realize that. It was complicated to me when I first got my eyes on it. But I beg you to very carefully trace through this code with your own numbers and look. This is just setting simple variables. And then while your low value is less than or equal to your high value, there's no gap in between, that there's something to look at. And then all you're doing is splitting the list in half. Low plus high, 0 plus 200 divided by 2 would be 100. That would be the middle of our 200 list. Okay, and then we set the item equal to the number in the middle, and then we test. Is it equal? Yes. Oh, great. Then go return. But we're never that lucky. So is it greater than? Then reset the high to middle. Is it less than? Then reset the low to middle. And you keep taking your range and cutting it in half. So go through this code. Run through this code and understand what it's doing. Okay? Try different numbers. Try different things so that you can see how efficient it is. I mean, you can see, this little piece of code right here makes it plain as day that if I had 999,999 and I was doing a linear search, my worst case scenario is 1 million lookups. All right? If I do a binary search and I do a worst case scenario, that's what I did right here. With a binary search, I looked for a number on the fringe, a super outlier, and it only took me 19 lookups to get there. Okay? That shows you the efficiency of a binary search versus a linear search. 20 versus 1 million. So the higher you go, the more efficient the binary search becomes. So that it's an important concept and it's an important little piece of code to look at. Believe me, I know because I've been there. It may look a little kooky to you at first glance. Go through it. Trace through it. List all the variables, and as you trace through the code, write down what you're looking at and what you're doing and see how it works. And then I'm going to put this code up on Sakai for you. So you'll even have that little linear search thing there. And you will see your second programming assignment is going to use a binary search and a linear search. Go ahead and use what I'm giving you. I have no problems with it. You'll see that assignment. You're going to have to grab some random numbers. You're going to have to clean them up, and then I'm going to want you to search through those numbers using these algorithms. You can take the code, use it. I need you to understand it. And through the assignment, you'll be able to understand it if I give it to you. All right? So that's basically what binary search is about. You're running through a list that's been sorted, and you're cutting it in half every time if you're not finding what you're looking for. And it makes things easy. And here, I think I used this when I used that code that I just showed you when I created these slides. So I'm running through my counter and my step counter here. Okay? If you don't understand this, get your butt to the cave. I'm serious. Go there, ask me if I'm around or one of my kids for help in understanding this stuff, because this is an important concept. And like I've said in the past, the first 3 units, you were learning Python. Now you're using Python. This isn't teaching you anything about syntax or anything that's particular to the Python programming language. You're Python programmers now. That's done with. That's out the window. Now you're using it. So now you're going that level higher, and you're going to learn how to implement these different algorithms. And doing a binary search algorithm is an important part of that. And as you study that code and you realize what's going on, you'll be like, you'll have that eureka moment. I promise you will. And it will be very cool. Okay? And guessing this will happen in a YouTube video? Yes, it does, because this is what you're getting right now. So we did the linear search. We did this. Everything is good, okay? So if you have a big list, you definitely want to get it sorted and sorted efficiently, because once it's sorted, well, then you can search through it and you know something about it, and it's much easier to handle than some unwieldy, unsorted list that you don't know what's going on. All right? So I ran through this. Now, the very last thing we're going to do before I wrap up and get out of here, because I'm exhausted and everybody's coming back tomorrow, so I got to actually cook a bunch of empanadas and make some pierogies. Saturday will be pierogies and empanadas, so there will be nothing even remotely healthy eaten tomorrow. You saw how we talked about linear search and how it's really long, and its worst case scenario is based on the length of the list, or n. We also looked at binary search, and basically binary search, if you analyze the algorithm, you find that it's what's called log n. And if you remember from your math classes in high school and all that stuff, log n is kind of the inverse of exponentiation. So you know how exponentiation gets really big really fast? Logs are kind of the opposite. Logs take really big things and make them small really fast. And that's the kind of efficiency you get when you examine binary search algorithms. Basically, Big O, oh yeah, you probably don't know who Oscar Robertson is. He played basketball in the 60s, and Big O there is from anime. But Big O, like I say here, is just for order of magnitude. Usually we throw out all of the different parts of the polynomial except for the biggest exponent, and we say that's the magnitude of whatever the number is we're looking at. Now, if I have a program that says print hello, I'm going to have what's called a constant Big O, because no matter what my input is or what my thing is about, it's always going to be the same because I'm always just printing hello. So that's constant, or Big O of 1. When you have a task that maps to the size of your data, like linear search, that is called Big O of n, because whatever your n is, think n population and statistics. If my list is 200, then n is 200. So my worst case scenario is 200 lookups, just like we did in the example when we looked at our sorts. If I'm looking at a list of 1,000,000, my worst case scenario is 1,000,000 lookups. Okay, so that's the Big O for a linear search. Now, if you have a list of 1,000,000 items, your Big O for a binary search is 20, because we just did it. Okay, that's pretty efficient. It's much better than n. It's linear, and if you look up, I think I could grab this graph from Wikipedia. If you look up the different Big O notation complexities for different algorithms in computer science, you can see down here are the two that we're dealing with, basically, because you have O of 1 is constant. We just talked about that, just printing something. And then O of log n, this right down here, it's right along the line. Okay, that's binary search. Now, linear O of n is the green right here. It doesn't look much worse here because it's not. Because if you look at the scale, you see how that's 100 in your operations and that's 100 in your elements. So it's kind of the scale is off. So it doesn't look very big, but if these were equal, you would see it would cut right up the side. So that is a linear search and that is a binary search. Now, some of the more interesting things you'll learn about if you ever study computer science and complexity is look at these guys. With just a small amount of elements, they fly off the charts for the operations, because that's when you get to Big O of n factorial, and that is called Combinatorial Explosion, and that is when everything has to be multiplied with everything, and you get problems like the traveling salesman problem, and you get big problems that in computer science cannot be solved. And it's not that they can't be solved logically, but some of them get so big that you don't have enough memory and enough time in the universe to tackle them. And those problems are usually called what we call intractable. There's just no way to get a handle on them. An interesting one to look at is the traveling salesman problem. We actually have people in the computer science department who did work on TSP, or the traveling salesman problem, in the 90s. And it's very interesting. And basically the problem is if you're a traveling salesman and you have 15 cities, then you have to find the shortest route between the 15 cities. Go. And to someone who's never thought about it, that may not sound like a huge problem. But if you start to examine how to tackle that and determine what it is, it's a monstrous problem. And it's very difficult to wrap, and it very quickly becomes almost impossible to wrap your hands around. So that's some interesting stuff. The stuff we're dealing with, linear search, binary search, is more tame, as you can see down here. They're certainly more efficient things, but things can get crazy with algorithms and the analysis algorithms, and trying to solve certain problems that just don't lend themselves to being solved in efficient manners. So trust me on this. You do not have to understand the math behind all of this, and you do not have to now run off and quick do log tables, and you don't have to know everything about Big O complexity. Like you hear me say all the time, I want you to be exposed to this stuff, So when you hear people talking about it, you understand what they're talking about, and you have an idea what ballpark you're in. I don't expect you to run out and become complexity experts. And I don't expect you to look here. Hold on. I don't expect you to run out and start reading complexity textbooks or even having them laying around your dining room like a sick person like me. I just want you to be exposed to this terminology and to some of these concepts so you know what's going on. There may be one complexity question on the Unit 4 quiz, and it will be ultra simple. There will be nothing kooky about it. All right? So do not worry about complexity. I just want you to see some of the terms and see what's going on with it. All right? I also, I listed some of the other stuff I think they had at Wikipedia. And that's it for this particular slide. This is about halfway through the slides, if I'm not mistaken. And that's basically everything but recursion. I do recursion with a separate video, and I'm also going to do some stuff on recursion when we meet in person at the end of the month. But that's it. That is the first review video for this Unit 4. Read those slides, understand what's going on with sorting and searching, then go to the resource folder for Unit 4, and I'm going to give you the binary search code. There may even be binary search code in there already. I'm just going to give you the new and improved with the coded up linear search. And it's all there for you. I want you to understand it, trace through that binary search code, and get your head wrapped around it. And then when you have a chance, look at the analysis algorithm stuff. Maybe read the Wikipedia page, reread the slides, and just get a handle on what I'm talking about when we talk about those things. When I compare the linear search to the binary search, that should help you out, because the linear is n, it's based on the length of the list, and the binary is much, much shorter. It's logarithmic in scale. Announcements. Let's see about announcements. We got to get back on track because it's the end of spring break, and I purposely kind of tried to take it easy because you need a break, and that's what it's there for. So I wanted to make sure that you guys were able to relax a little bit. Unit 3 is kind of long and kind of stressful, and the homework assignment is bang. It's the first time you get that really hard one. And then it's the first time you get an assignment where you can't go online and look up my past videos and find out the answer to it as well. So for a lot of people, it's like, oh, wait, I have to actually do this? Oh, no. So I know Unit 3 is a pain. I get it. But now you've already been through Unit 3, so you've been disaster tested, and you will be fine. You know exactly what to expect, and everything is going to be cool. That said, I'm going to start getting you stuff over the next couple of days. I'm getting you this video. I may post it tonight. I may post it tomorrow morning, Saturday morning. I'm going to get you assignment 1. For whatever reason in this unit, things are done backwards. And the homework assignment I'm going to give you is for recursion. And then the second assignment, which is a little bigger, I'll probably give you Sunday, is the one that deals with linear search and binary search. And you'll be able to utilize a lot of the code that I'm going to give you tonight in order to do that assignment. Then a new wrinkle. I'm going to be giving you a third assignment, but it is optional. It is your first extra credit assignment. I think if you notice, if you go through the Unit 4 slides, there's no little extra credit points laying around. It's because I give you a full-bore extra credit assignment. And the assignment's pretty easy once you prepare your system. But the problem is preparing your system. Because what you're going to do is you're going to load a third-party module or library called Matplotlib. And you're going to get Matplotlib working on your system. And then you're going to use it to create graphs with the random number file that you use in the second assignment. And if you do that, you'll be able to get, I forget what it is, 4 or 5 points, maybe 5 extra points. So those of you who are floating in that A, B, Schrodinger's cat area, and you want to collapse that probability wave and make it an A, do these extra credit assignments. There'll be another one down the road when we start doing things in Unit 5. But this is the first one. And it's good. And you'll hear me say this a bunch of times, and you'll hear me say this when we meet in person at the end of the month, is that part and parcel of being a Python programmer is learning how to deal with installing modules on your system and using them in other places. And I mean, when it comes to Python, at the end of the day, everybody uses NumPys. Everybody uses SciPy. Everybody uses Pygame. Everybody uses Matplotlib. It's free MATLAB for Python. Everybody uses Panda. Everybody uses the scikit. So you're probably going to need to know and learn a bunch of stuff about that too. That has stuff to do with machine learning. But if you're going to do data science, you need to know that stuff too. So another popular library nowadays is called Beautiful Soup. Beautiful Soup allows you to scrape the web and read in web pages and be able to sort all the different data in web pages by their tags. So that's another good library to learn. So we're going to start to venture into that world a little bit in this unit and get Matplotlib loaded up, okay? I also have realized that the day we meet for class is also the scheduled end of the unit, and I don't like that. I think there should be an extra couple days at the end that you have time to work and time to do assignments and blah, blah, blah. So I'm going to change that. Well, I haven't done it officially yet, and I'll do something on it next week when I get back to work and I get back into the swing of things. But the last day of the unit isn't going to be the last day that we have class. I'll give you a couple days after that, and we'll start Unit 5 a little bit later, okay? Keep in mind that you should be getting together with your group mates and putting together plans to do the proposal for the project. Because if I'm not mistaken, the proposal is due at the end of this month as well. I hope you've been reading the announcements and you've gotten all the information on the final project and understand that that's got a few different components to it, and the first one is due at the end of the month. Okay? So it's a little early in the game, but don't forget that about 2 weeks from now, we're going to meet. We're going to have a class meeting at Core Auditorium, our third of 4 class meetings. That'll be fun because we'll do announcements. We'll talk a little bit, and then I'm going to review recursion with you because I like to review recursion in person, and I like to, do different diagrams to make sure people understand what's going on with recursion and it doesn't freak people out. All right? Then I'm going to get out of here because it's getting late. I bet you this one went long. I'm scared to even look. And I got to get some sleep because it's almost 2 o'clock. And all my friends are going to be back at noon tomorrow because I forget what game. Oh, I think it's Miami and Wichita State is the first game tomorrow. There were a lot of good games tonight. If you like basketball and you like college basketball, there were a lot of competitive buzzer beater games. Northern Iowa won their game, and Iowa won their game in a weird way at the end, and St. Joseph's ended up beating Cincinnati, and it was a really interesting, fun, cool night if you like basketball. And if you don't, who cares? Like Python. That's the important part. All right? Then I'm going to get out of here. I'm going to get some sleep. I will get you your homework assignments over this weekend. I will get you, hopefully, the second review video sometime in the next 48 hours. I will get you this one as soon as possible. Because I realize the snow is coming, and it's going to be fun if you get stuck at home on a snowy, weird Monday to sit in front of your computer for a couple hours and catch up with your Python. So I want to make sure you have all these resources so you can do something like that, not just say, I already read the slides, I got nothing to do, blah, blah, blah. All right, so you be good, and I will talk to you very soon. All right, later.